Okay, good morning. Today we are going to see the basics of terminology related to psychometry. Now, when we say psychometry, so remember psychometry is completely related to air. And in air, it is assumed that it is a mixture of dry air and water vapors. Forget about the other elements. So basically it is talking about the air, that is a mixture, wet air. Then it is talking about water vapors inside that air. Then it talk about a dry air, its superheated condition, its saturation condition. All these things we are talking and try to draw the various processes by using their psychometry to identify the various other properties. So before that, we must know some terminology which we are going to use to plot our psychometric process. So the basic terminology we will start, that is, first is DBT. So what is DBT? So DBT is stand for dry bulk temperature. So as I said, the psychrometry is related to your air. It is not related to any specific fluid, liquid or other gases. It is specifically for air. So in air, that means presume that is the atmospheric air, suppose. And I am using a thermometer. So whatever be the mercury thermometer, a very well-known common device to measure a temperature. So this is a mercury thermometer. We know that at the end of mercury thermometer there is a bulb. And this mercury thermometer is calibrated in terms of scale of temperatures. So if you calibrate this in Fahrenheit, so it will show the temperature in Fahrenheit. If you calibrate in Celsius, so it will show the temperature in Celsius. And in this thermometer, we observe that there is a mercury filled in this bulb. Now suppose I am using such thermometer to measure the atmospheric air temperature. So if I keep as it is, that means this bulb thermometer, bulb, this is actually called a bulb. If this bulb is naked without wounding any material, any cloth, anything, so if I am using such bulb, so it is called a dry bulb. And in this, when I try to measure the temperature, so whatever be the surrounding air temperature is there, suppose this is the air. So whatever be the temperature of this air, and already I said air is nothing but a mixture of water vapor plus dry air. So this bulb will expand its mercury content and the mercury will rise through its capillary and it will expand till it's come in a equilibrium. So suppose this air having this temperature, suppose 40 degrees centigrade. So this thermometer is going to read what is the temperature of this air. by showing the expansion of this mercury in a capillary tube, and this thermometer is calibrated suppose in degree centigrade. So whatever be the height gained by this mercury, it is showing that much is the temperature of this air. Now this temperature, measured temperature 40 degrees centigrade, is using by this conventional thermometer, which is not cover the thermometer bulb by any material, any substance. So it is a naked, you can say this is a dry bulb temperature. So 40 degrees centigrade is a dry bulb temperature. So it is a measuring a temperature of directly air by this thermometer. Now imagine there is a second terminology, that is wet bulb temperature, that is denoted by Wbt. This is called wet bulb temperature. Many students know what is dBT, what is Wbt, that is dry bulb temperature, wet bulb temperature, but they fail to explain what is the need of wet bulb temperature, what is the significance of wet bulb temperature. If we are able to measure the air temperature, then why we go for this Wbt? So let's see. Suppose the same thermometer I am using to measure air temperature. Again, I am saying air is a mixture of dry air and water vapors. This is calibrated in terms of degrees centigrade. So it will show the temperature in degrees centigrade. This bulb, same thermometer. I am not using any different thermometer, modified thermometer. I am using the same thermometer, and this thermometer put in air. Again and again I am repeating, this psychrometry belongs to air, which is a mixture of water vapor and dry air. We are not talking about any other gases. We are talking about air only. So this is the air, which is a mixture of water vapor plus dry air. Now imagine I provide a wet cloth. Suppose taken, and this wet cotton is wrapped on this bulb. So I provide a wet cloth. So basically it is cotton immersed in a water. तो ऐसा जो भी कॉटन मटेरियल है या यू कैन से क्लॉथ पीस आपने भिगो दिया वाटर में और उसको रैप कर दिया इस बल्ब पे. स्टार्टिंग में आपने जो एयर टेम्परेचर लिया था वो एटमॉस्फेरिक एयर गिनने के लिए लिया था और इसका एटमॉस्फेरिक टेम्परेचर आपने गिना तो इट इज 40 डिग्री सेंटीग्रेड. सेम एयर आपने नेक्स्ट टाइम क्या किया, इस थर्मामीटर बल्ब को वेट कॉटन से या वेट क्लॉथ से सराउंडेड कर दिया. अब ये जो एयर है जिसका डीबीटी टेम्परेचर आपने गिन लिया था 40 डिग्री सेंटीग्रेड, अब ये वेट क्लॉथ की वजह से होता क्या है, इस एयर के अंदर जैसे ही ये एयर का टेम्परेचर कब गिना जाएगा, जब ये एयर इस थर्मामीटर बल्ब को कांटेक्ट में आएगा. So जैसे ही ये एयर इस बल्ब के कांटेक्ट में आएगा तो दिस टाइम इट इज नॉट कम डायरेक्टली इन अ कांटेक्ट ऑफ मर्क्यूरी बल्ब, इट पास थ्रू दिस वेट क्लॉथ. अब जैसे ये वेट क्लॉथ के अंदर जाएगा एयर, तो होगा क्या है, इस वेट क्लॉथ का जो भी मॉइस्चर है वो इस एयर के अंदर आ जाएगा। अब एयर के अंदर कैसे आएगा, तो जो भी इसका टेम्परेचर है एयर का, सो उस टेम्परेचर पे जैसे ये क्लॉथ के अंदर जाएगा एयर, तो ये क्या करेगा, उस वाटर को लैटेंट हीट देगा। तो एयर में जितना भी टेम्परेचर था उसमें से थोड़ा सा टेम्परेचर ये उसको कूल डाउन करने में चला जाएगा। दैट्स मीन सॉरी, इट एब्सॉर्ब द मॉइस्चर। लेट मी क्लियर अगेन। सो ये जो भी एयर है, ये जैसे ही वेट क्लॉथ के अंदर जाएगा तो इसके अंदर मॉइस्चर, वाटर वेपर्स, ड्रॉपलेट्स ऐसे ऐड होंगे। अब ये ऐड होंगे तो क्या होगा कि इसका टेम्परेचर रिड्यूस हो जाएगा। सो वाटर ड्रॉपलेट्स, वाटर वेपर्स क्या करेंगे, आपकी इस एयर का टेम्परेचर रिड्यूस करेंगे। अब कैसे टेम्परेचर रिड्यूस करेंगे, इमेजिन दिस इज air droplets, air molecules. We are thinking at a micro level. So this is air molecules, and suppose this is water molecules suspended. So we can say water vapors. This is having 40 degrees centigrade when we measure it with dry bulb temperature. 40 degree when we measure it with our regular thermometer without covering this mercury bulb. Second time we cover this mercury bulb with a wet cloth. At that time, what happens when air enters? So water vapors, water droplets, or you can say water content that is in a vapor form. So it is called a moisture. So moisture get added. Previously, these are the air molecules. And it having a moisture, but the moisture content is less. Just a minute. Now when this air come in a contact of this wet cloth, so its moisture will added into this cloth, this air. So moisture content will increase. So now water vapor content is increased. The same volume, same air, but when it come in contact of wet cloth, so water moisture that is absorbed in this air, and due to this its temperature decreases. Now this cooled air having a higher moisture content is come in a contact of this mercury bulb. Now definitely mercury will sense a less temperature, and suppose this is showing 30 degrees centigrade. Why the sensing temperature is decreased? Because addition of moisture cool down your air, and that cool down air come in a contact of this your mercury bulb. So accordingly it is showing a reduced temperature, and this reduced temperature is known as wet bulb temperature. The air is same. First we measure with a naked mercury bulb, so it is showing 40 degrees centigrade, so we are saying it is a dry bulb temperature. Second time when we apply that wet cloth on the mercury bulb, and then we are measuring the same air temperature which supposed to be a 40 degrees centigrade, but this time due to this wet cloth, your air get cooled down when it actually come in the contact of mercury bulb, and then after we saw the temperature level is decreased, and this 30 degrees centigrade is the temperature of this air. But when applying this wet cloth, so this reduced temperature is known as wet bulb temperature. Now what is the significance of this? Both are showing the air temperature. One is a dry bulb temperature, second is a wet bulb temperature. Now what is the significance of this? Why we are using wet bulb temperature? We know that the dry bulb temperature can read the temperature of air. Why we are using this? Now imagine the same air. Suppose this air is a mixture of water vapors. Suppose water vapors is 40% and 60% is a dry air. Due to this wet cloth, the air come in actual contact of this bulb having the water vapors. Now 40% get increased by 50% due to addition of moisture, and dry air remain 50%. Suppose anyhow I increase this wet cloth, or I increase the water content of this wet cloth. So what happened? Water vapor content will be increased. Suppose next time it becomes 70%. So your dry air remains 30%. So initially water vapor 40%, so showing 40 degrees centigrade. When your water moisture get added due to this wet cloth, we observe 30 degrees centigrade. If I increase this wet cloth size and water content, so I observe that the water vapor content is 50 degrees centigrade, dry air 50, so definitely its temperature will again reduce. If I added a moisture, suppose now moisture content is 70%, dry air is 30%, so again my Wbt will decrease. So this Wbt is depend on how much moisture content in that air. So by using Wbt, we can predict the air quality in terms of water vapor, the humidity. For that we use Wbt. Now imagine the capacity of this air to absorb the water vapor gets saturated. Now externally we can't add the moisture because already air is saturated. Whatever be the ability to absorb the moisture is get saturated. Now if I try to add any droplets, any molecule of the water vapor, then it will condense out. That means saturated air. At that time, whatever be the Wbt, it is showing saturation temperature. So saturated air temperature will be Wbt. So the content of moisture in air, accordingly Wbt will react. Accordingly we get a Wbt temperature. So the significance of using Wbt, it is relating with your humidity content in air. Next, the final term regarding Wbt and dBt is Wbt depression. So, wet bulb depression. Actually, the Wbt, it is not a wet bulb temperature depression. It is wet bulb depression. Depression means how much it reduce, what is the difference. So Wb wet bulb depression shows the difference of dry bulb temperature and wet bulb temperature. So wet bulb depression showing the difference by using this wet cloth. So these three terms are very important. We have to use the dBT, Wbt when we are plotting any process on psychrometry chart. Next term is relative humidity. So hopefully it is clear now what is wet bulb temperature, what is its significance, why we are using wet bulb temperature, because it is directly given an idea about the humidity content. So more addition of water vapor or humidity, it will reduce Wbt. Now we will see the second term. Next is relative humidity. Humidity is nothing but a content of moisture, content of water vapor. Now relative humidity, and it is denoted by phi. What is the relative humidity? So it is nothing but a mixture of actual moisture in air. So phi is a ratio of actual moisture air divided by the maximum possible or maximum moisture if we are calculating relative humidity, so it will be always in percentage, so multiply by 100, so it will give a percentage. Now what it means? Suppose this is a portion of air, this portion I am analyzing, and these are the dry air molecules. If I add all these masses of dry air, so we can say it is the mass of air, dry air. Now, suppose I measure the humidity content. So this is water vapor. For example, for the sake of example, to understand the concept. So this is mass of vapors. Mass of vapor shows by star, it is total count wise 4. Mass of dry air shown by circle, hash 1, 2, 3, 4, 5, 6, 7, 8. So mass of dry air is 8. So this is the air mixture having a dry air as well as water vapors. Now, this 4 water vapor count wise is the actual moisture in this air. Now imagine 4 is not the maximum limit of absorbing the moisture in this air. If I am adding a moisture, so it will absorb in this air. Now 5, 6, 7, 8, 9, 10, 11. Now it gets saturated. Saturated means if I try to add any moisture, it will not absorb in this air, but it will remove out. If I try to add one moisture, then one moisture will be removed because it reached to saturation condition. So when it reached to saturation condition, that means addition of any extra moisture will not absorb in this air. It will not remain as a mixture of air and water vapor. It will remove out, condense out. So this saturation condition, when it reached to saturation condition, I observe mass of water vapor become 11. Mass of dry air is 8. At the beginning, when I measure, so that time mass of water vapor is only 4. That is the actual water vapor contained in this dry air. But when I go on increasing a moisture, so I observe when moisture becomes 11, it gets saturated. That means this air can hold only maximum 11 water vapor. So this is the maximum capacity. So from this, I come to know that what is the relative humidity. So actual moisture in air, in our case, it was 4. And the maximum moisture air can hold, that is 11. So whatever with this ratio 4 by 11, this is showing a relative humidity. So it is simply the actual condition moisture contained in air and the maximum possible moisture contained in that air. So this is called relative humidity. Now come back to our previous part. Now imagine relative humidity. It is also written as RH. So relative humidity, suppose I am increasing relative humidity. That means actual moisture content of air is increased. So if relative humidity increase, wet bulb temperature. What happened to wet bulb temperature? So no doubt, relative humidity increase, that means adding a moisture, its temperature will reduce. In that case, wet bulb depression, which is nothing but a dVt minus Wbt. So dVt will be the same, but Wbt will reduce. So difference will increase. So wet bulb depression will increase. So remember these things. Relative humidity increases, wet bulb temperature reduces. If wet bulb temperature reduces, so that this difference will be increased. Many times it is asking your oral exams such kind of questions. You can reverse this also. If relative humidity is decreased, wet bulb temperature will increase, and this wet bulb depression will decrease again. So this is next term, relative humidity, which is showing the actual moisture content in air to the maximum possible moisture content in that air. And maximum possible moisture content, that means when air reach to a saturation condition. Saturation condition means when addition will not accepted by the air, it becomes saturated. Next term, it is specific humidity. Now the specific humidity, it is known by many terms. So I will write all that. Specific humidity, also known as humidity ratio. It is also known as absolute humidity. And it is denoted by W. Now, what is the specific humidity? So, specific humidity can be defined as a ratio mass of water vapor in wet air wet air I am specifically mentioned because air is a mixture of, or we can say simply air. It is a mixture of water vapor and dry air. So mass of water vapor in air to the mass of dry air. So in short, specific humidity is whatever be the mass of your total air, in that total air, what is the amount of mass of vapors and the amount of mass of dry air. If I add these two, mass of water vapors plus mass of dry air, then it becomes a total mass of air. So what will be the total mass of air? If I take a ratio of mass of water vapors to the mass of dry air, then it is called specific humidity. The relative humidity is different thing. It is relative humidity is showing in relation to maximum possible moisture content of that air. What is the actual moisture to the maximum possible moisture? That is the relative humidity. But specific humidity, it is showing what is the mass of water vapor to the mass of dry air in total content of air. So this is a specific humidity. Now, many times it is said that the specific humidity is a function of partial pressure of water vapors only. So, specific humidity is a function of partial pressure of water vapor only. And they are asked to justify this. How this is possible? How it is justified that the specific humidity is a function of only a partial pressure of water vapors. Now let me explain basic theory. When I am talking a total mass of air, so it means there is a mass of dry air which is written as small ma plus mass of water vapor which is written as mv. So when I am talking about the pressure, so total pressure exerted by this total mass of air will be P. So it will be the addition of partial pressure of dry air plus partial pressure of this water vapor. We know that Avogadro laws. So partial pressure exerted by this dry air content is a PA, pressure exerted by this water vapor is a PV. So if I add this partial pressure, so it will be equals to the pressure exerted by the total mass of air. Now come back to our point. We have to justify the specific humidity is a function of partial pressure of water vapor only. And we observe here, there are a partial pressure of dry air as well as water vapors. So if I am taking any air, any mass of air, so definitely there will be a dry air portion and water vapor. Definitely there will be a partial pressure of dry air and partial pressure of water vapor. But the statement is, it is simply dependent on water vapor only, and we have to justify this. So specific humidity W, which is the ratio of mass of vapor to the mass of air. Now anyhow we have to justify this. So total mass of air, if I am taking a ratio of total volume of air, I will written here. So this is the total volume of air, V. And if I divided this total volume with the mass of dry air, so it will be a specific volume of dry air. So total volume divided by mass, so it becomes specific volume. If I am dividing this total volume of air by mass of dry air, so it becomes specific volume of dry air. In the same manner, if I divide this total volume of air by mass of vapor, water vapor, so it will be a specific volume of water vapor, and it will be denoted by V suffix V. Now we have these terms, mass ratio. So we will convert into a volume, specific volume ratio. So V upon MA is a VA. I want to find out the value of MA. So MA will shift. So MA on this side I will write this. Okay. So MA, what is MA? So MA is V upon VA, and V is V upon VB. Replacing these masses in this specific humidity. So W will be V by VB divided by V by VA. So on simplifying, we observe that VA upon VB. So it becomes a specific volume of air divided by specific volume of water vapor. So specific humidity can be written as the ratio of specific volume of air to the specific volume of water vapor. In terms of mass, It is the ratio of mass of water vapor to the mass of dry air. Now, in terms of volume, so specific volume of dry air to the specific volume of water vapor. Now, anyhow, we have to change this specific volume in terms of pressure, because we have to justify how partial pressure of water is only the function of specific humidity. So now we will have to replace this by pressures. Now the very well known, the general equation PV is equals to nRT. And now suppose n is 1, n having the value 1. So it is PV is equals to RT. If I am talking about a dry air, so it becomes partial pressure of dry air, total volume of air divided by the molecular mass. So molecular mass of dry air is equals to RT divided by, so I am dividing both sides with the molecular mass of dry air. Now total volume divided by molecular mass, so it becomes a specific volume of dry air, RT upon NA. Now what is this PA? It is a partial pressure. And we are interested in replacing specific volumes. So specific volume will be RT MA PA. If I did the same thing for water vapor, so I observe that PV V upon molecular mass of water vapors, RT molecular mass of water vapors. So this becomes PV specific volume of water vapor, RT upon molecular mass of water vapor. So VV will be RT upon MV into PV. So we have now the value of VA and VB, specific volume of air and specific volume of water vapors. Now putting the values, so specific volume W is specific volume of air RT upon MA PA divided by VV, so RT MV PV. So this get cancelled. So specific humidity is mV upon MA multiplied by PV upon TA. Now the question is, what is the molecular mass of vapor and molecular mass of air? So molecular mass of vapor is 18 point, definitely it is talking about the water vapors. So molecular mass of water vapor is 18.016 kg per kmol, and molecular mass of air is 28.966 kg per kmol. So if I put this, so W will be 18.016 divided by 28.966 multiplied by partial pressure of water vapor divided by partial pressure of dry air. If I simplify this, I reach to a final form, specific humidity will be 0.622 PV upon PA. But still we are unable to say that the specific humidity is the only function of partial pressure of water. There is a partial pressure of air also. Now we know the total pressure of air will be the addition of partial pressure of air, that is dry air, plus partial pressure of water vapors. If I am replacing partial pressure of dry air, so it becomes P minus P of partial pressure of water vapor. So I am just replacing this PA. So specific humidity is 0.622 PV divided by P minus PV. Now what is this P? P is the total air, mass of air. So it is the pressure of total air. If I am measuring the pressure of this room air, so it will be an atmospheric pressure right now, this at this particular location. So it remains constant. So atmospheric pressure will be changed according to height only. For right now in this classroom, if I am measuring atmospheric pressure, so at any corner, any point of this classroom, it is constant. This term is a constant, 0.622 numerical value, constant. This P, total pressure of air, is constant. So what is the remains? Remains is only the partial pressure of water vapor. So can we say the specific humidity is simply a function of only the partial pressure of water vapor? So hence true. So whenever it is said that how you can justify the specific humidity is a function of only the partial pressure of water vapor, so we have to do all these exercises and we have to reach this equation, and from this equation we can justify. Now we can say the specific humidity is a function of partial pressure of water vapors only, not a partial pressure exerted by dry air. So hopefully this point is clear. Now last 2 points are there. So once we cover all these basic terms and concept, so next lecture we will go for processes. How to plot the processes on psychrometry, how to calculate the respective data. Now the next is degree of saturation, or we can say percentage humidity. So degree of saturation. So there are two definitions. It is the ratio of actual mass of water vapor in a unit mass of dry air to the mass of water vapor when it becomes saturated. That means the maximum water vapor can that air hold. So that is called the specific humidity, actual specific humidity. So water vapor contained by any dry air, that is a specific humidity. And second, water vapor contained by any dry air at the same temperature when it is saturated. So we can say the degree of saturation, which is denoted by mu, is specific humidity actual. So mass of vapor contained by mass of dry air to the mass of vapor contained by mass of dry air at same temperature when that air reach to saturation. So it is nothing but a ratio of specific humidity of air to the ratio of specific humidity of the same air at same dBT temperature when it reach to saturation point. Now, to elaborate this, I will go for TS diagram. We know there is a dome. I am talking, suppose this specific humidity at dBT 40 degree centigrade. So saturated specific humidity of air when it is saturated, but the temperature should be the same. I can't change the temperature. So at the same temperature, same mass of air, when the actual specific humidity and when the saturated air specific humidity at same temperature, that's the temperature remains same. That means when I am plotting this, so suppose this is the temperature 40 degree. So this is the constant temperature. Now when I am plotting this, suppose this is point P, PV. No doubt when I draw a PV line, so pressure line will be like this. I have to keep the temperature same. So what I am doing, my air is at this point, I am adding a moisture. So moisture will add. As the moisture is added, its moisture absorbing capacity will reduce. Again I am adding, its moisture absorbing capacity will reduce. I am keep adding the moisture, its moisture absorbing capacity will reduce, and it will reach to saturation point. And we know that what is the meaning of this curve? This is a dry saturated vapor line. Vapor line or curve. That means after this, there will be a separation of liquid. So in this dome, there is liquid plus vapor mixture. So it is called wet zone. After this, there is a water vapor and dry air, but there is no traces of water particles. It is in a vapor form. Water vapors are there, but when I move ahead of this dry saturation line, so I observe that there is a separation of water vapor. Water particles will be separated out. So it is a mixture of liquid water plus dry air. So at this point, this is the maximum possibility I can absorb the moisture, and this is called PS, pressure at saturation point. So pressure of vapor, I am keep adding a moisture, so it will reach to a saturation point. If I am plotting a pressure line here, so this will be a pressure line. So this will be a saturation pressure. The dBT temperature is same, but I am adding a moisture, so moisture absorbing capacity will reduce and it reach to the maximum possible water vapor can that air hold. If after this I am trying to add anything, it will be separated out as a liquid. It can't absorb the air. So at this point, what will be the specific humidity? That is Ws. At this point, this is the actual condition that will be a W. Now the last term is dew point temperature. So what is a dew point temperature? There is always a confusion between a dew point temperature and this concept. So again, TS diagram, but this time for dew point temperature. So drawing low. Now my air is at this point. This is PV and this at a temperature this T. If I try to draw this pressure line, so pressure line will be like this. Now, at this point, there is certain amount of water vapors along with remaining amount of dry air. In this, I am not adding moisture. In this condition, I am adding a moisture, temperature remains same, but at some point, certain point, it will reach to maximum possible capacity of air to absorb the moisture, that is called saturation. Now, I am not adding any moisture, but I am decreasing temperature. At this point, temperature will be decreasing. The moisture content is same, but I am reducing temperature. Moisture, I am not adding or removing, I am just reducing temperature, so temperature will be less. Again decrease, decrease. And one time it will reach to such temperature when your vapor reach at this dry saturated vapor curve. So moisture I am not increasing or decreasing, I am just simply reducing temperature, and one time I reach to such condition where my air reach at exact dry saturated vapor curve, this point. After this, if I try to reduce a temperature, no doubt your curve will be inside this dome, and inside this dome, as soon as vapor enters inside this dome, it will be liquefied. That means moisture get condensed. So the temperature where moisture get condensed, water vapor get condensed, that is called dew point temperature. So the dew point temperature is the temperature at which the water vapors start condensing. Liquid conversion takes place. That is the dew point temperature. Above this dew point temperature, it remains as a water vapors. Below this dew point temperature, no doubt, your water vapor will condense and convert into liquid. So here I am reducing temperature, not removing or adding moisture, but here I am adding moisture, so it reaches to this dry saturated vapor curve line. Here, by reducing temperature, it reaches to dry saturated curve line. And the point where it reaches to dry saturated curve line, the lowest temperature at which it remains as a vapor, below which it starts converting into liquid, that is called dew point temperature. The lowest pressure, after which I observe the separation of liquid, that is called saturation. I can't absorb more moisture. If I try to add the moisture, it will separate out as a liquid. That is called saturation condition. So this is the terms we have to consider when we are plotting any process. Now the last point for today's session are 6 diagrams, psychometry, basic. We must know how that psychometry is drawn, because in a glance it is very difficult to read psychometry chart because it having a number of lines. So basically this is the shape of psychometry chart. So how to draw? Draw a small line, small vertical line, then this side also horizontal, and this quadrant we have to join by a curve. So always remember this is the shape of psychometry chart, and we have to talk about 6 different points. So I will draw 6 psychometric charts. And the last portion. So these are the basic shape of psychometric chart. Now, one by one. First is dry bulb temperature. So remember, dry bulb temperature is on this baseline. But this is not the 0 point. Little bit ahead, this is a 0 point. And then -5, then -10. On right hand side of 0, +5, +10, 15, 20. Likewise, it will reach to about 55. This is a dry bulb temperature in degree centigrade. So this is a dry bulb temperature scale on horizontal side, bottom side of this psychometry, and dry bulb temperature lines, if I observe, so it is simply the exact vertical line from all these points. So these are the vertical lines which is representing dry bulb temperature. So these are the vertical lines representing dry bulb temperature. Now imagine I am at this point. So what is the dry bulb temperature? So dry bulb temperature will be 30 degrees centigrade. If I am at this point, again I measure the dry bulb temperature is 30. So along this vertical line, dry bulb temperature is same. But if I shift left or right, then dry bulb temperature will be different. So all dry bulb temperature are vertical lines. Next, Wbt, wet bulb temperature. This line for dry bulb temperature, Wbt, wet bulb temperature. Wet bulb temperature are plotted on this curve section. So this is 0, 5, 10, 15, 20, 25, 30, 35. Nobody going to ask you to draw this psychometric chart, but we must know how these scales are there and how that lines representing that particular values, properties. So this scale is for wet bulb temperature in degree centigrade. DBT lines are exact vertical, but these wet bulb temperature are inclined, but parallel to each other. These all inclined lines representing wet bulb temperature. This curve represents saturation curve. Let's move ahead. That is humidity ratio or specific humidity. Specific humidity. Specific humidity is like on a vertical side, and it is always given in 3 digits: 0, 0, 0, 0.005, 0.010, 0.050, 0.020, 0.025, 0.030, 0.035, 0.040, like this. And the lines which are representing this humidity ratio or specific humidity are exact horizontal lines. So on a psychrometric chart, when you observe any horizontal line, so it belongs to specific humidity. Next is relative humidity. It is denoted by phi, relative humidity. Now, how to represent relative humidity? So, relative humidity is vertical lines. So, first vertical line, this is 10% relative humidity. Started from this, ended on this side. So 10%, 20%. How to draw? If anyone asking you to draw, so remember this side distance is reduced, this side distance is goes on increasing. So some lines reach to this vertical side and some lines reach to this horizontal side. 20% relative humidity, then 30%, 40%, 50, 60, 70, 80. Relative humidity, it is denoted by RH also. 90%. When relative humidity becomes 100%, that means it cannot absorb any more moisture. That condition is reached, and that is denoted by a saturation line. And this vertical line of this psychrometric chart, this itself belongs to 100% relative humidity. So remember, it is started from 10 and it will reach to this curve last portion of this psychrometry, and this curve line is itself is a 100% relative humidity line. Next, specific volume and enthalpy lines. Now we know that what are the enthalpy lines. So wet bulb line. So wet bulb lines will be here: 0, 5, 10, 15, 20, 25, then 30, 35, like this. So these are the inclined lines. This is wet bulb temperature lines. Now the enthalpy scale is given on this side. This is enthalpy scale. And the enthalpy line is exact parallel to this wet bulb temperature line, but little bit on a higher side. So draw such lines. These belongs to enthalpy lines. It is not overlapping to Wbt. So this will be an enthalpy line. So what is the value of this enthalpy? So we can measure what is the value on this enthalpy scale. So this particular inclined line having that enthalpy value. Now the specific volume, I am drawing on the same lines, the specific volumes. So it is also inclined lines, but the inclination is different. Like this, there is a specific lines, and it is started from 0.8 and it is ended to 0.95, and this is specific volume. So we must know all these lines, what it represent, how it is look like. Now the last point is a dew point temperature. So be careful, listen carefully. This is 100% relative humidity line. This is wet bulb temperature curve. So scale on this wet bulb temperature. And we know that when relative humidity is 100%, that means now we can't add a moisture. If I reduce the temperature below that, then the formation of liquid will start. That means dew point will be on this scale only. Whatever be the Wbt scale is there, that scale representing for dew point temperature also. Now, how it is representing? So, suppose these are the Wbt lines. Now, the dew point temperature. Suppose I have air having a particular dBT. Suppose this is dBT 40 degrees centigrade. Suppose. So, dBT line will be vertical. And this air having some specific humidity, suppose 0.030. This is specific humidity. Specific humidity line will be horizontal. So this is the intersection point. If I extend this till the Wbt curve line or 100% relative humidity line, so I observe that this will be the temperature higher than 10, lesser than 15. Suppose this is the temperature of 12 degrees centigrade. So when I extend this line horizontally, so I observe this temperature, and this temperature is a dew point temperature. So dew point temperature, there is no separate curve. It is measured on Wbt curve itself. So this is called dew point temperature. So today's all concept is over. Now in the last we simply observe how it look like when all lines are drawn as a psychrometry chart. So I am sharing a simply line drawn diagram. So this is a psychrometric chart look like. So horizontal lines, these green lines belongs to specific humidity, red lines belongs to DBT, these points on wet bulb temperature, these curve lines started from 10%, 20% relative humidity become 100 on this WBT curve line. Then this yellow color inclined line WBT lines, this sky blue color inclined line are enthalpy lines, and a little bit gray color inclined line are specific volume lines, which is in a range of 0.80 to 0.95. Unit is meter cube per gram. So this is your complete psychometry chart. When we have to plot any chart, any process on this psychometry chart, so we will get psychometry chart from exam department. We have to plot their process and find out the values. So hopefully about the basic terminology and lines, the concept is clear for psychometry.